Hello, everybody. I'm Richard from Ditto, and we are an offline-first SDK that enables and powers some really cool applications in some surprising contexts. And I'm excited to talk to you today. Today, I want to walk you through some key lessons learned, boil them down into some practical principles that you can apply to building local-first solutions, and show you how some of these ideas and principles work in the real world. So to start with, I thought about what was the one thing that I could share with everyone that would be like the most valuable lesson that I could share with you. The thing that I wish more product designers and software engineers knew earlier on that would save them a lot of trouble exponentially, throughout projects and even throughout their career. And it's this. So I want to rip off the Band-Aid and really start with a hard truth here. The happy path refers to the ideal or most simple flow of logic through a system. And I've worked with teams across different industries for decades, and some of whom have been tempted to focus on only satisfying the ideal requirements. And they've learned this the hard way. So raise your hand if you've ever heard someone say that they just want to focus on the happy path or simplify things. Yeah, exactly. And while the happy path can be a helpful starting point or a conversation point, it really quickly breaks down in real-world implementations, especially when there's distributed systems involved. And the reason that there's no happy path, it's these guys, edge cases. Edge cases are usually the first thing that you hit when you start developing an idea. And you kind of think, yeah, but what about? And it's that moment when you start building something that you thought was going to be easy, and then that feeling kind of sinks in and you realize, yeah, maybe it's not. Maybe you start jumping down some rabbit holes and trying to pull yourself out. So depending on your experience, this might be a really familiar feeling to you, or it might be something that you experience very rarely, but it is what I believe that keeps us hooked as software engineers, the thrill of solving hard problems. That feeling like, oh my God, what have I started? And followed hopefully sometime later by, Eureka, I figured it out, I'm a genius. So in the early days of mobile computing, mobility was mostly a novelty, right? You had music players, offline games, you had maps with no turn-by-turn directions. There were productivity apps like notes or shopping lists, and these were relatively straightforward apps compared to today's standards, because we returned to our desks to do the real work. So in the beginning, the cost of failure or errors in mobile software was relatively low. For example, if your web page failed to load, you could just try again. Or if you were Steve Jobs, you could just ask everyone to get off the Wi-Fi. If your Flickr photo failed to download, you could just wait. Or you could play an offline game like Bejeweled, Angry Birds, or Sally Spa. We were used to waiting. For those of you unfamiliar with iBeer, this was one of the first hit apps to make full use of the accelerometer. And that is to say that users had modest expectations and reliability wasn't a priority. But today that is very much not the case, right? Apps are deeply integrated into daily life, business operations, and even safety critical situations. Computing moved from the desk out into the real world, and that added a physical layer to software requirements. And it multiplied the number of edge cases. So most developers start out by building mobile apps that consume data from REST APIs. This approach just involves fetching data from the server and displaying it in the app. It's pretty straightforward, and it gets the job done for basic use cases. But when the app goes offline and the app can't fetch data, users are met with spinners, loaders, or error messages. For example, a commuter arrives at Liverpool Street Station, which has notoriously poor reception. They need to display their rail ticket, so they pull out their phone as they're jumping on the train, but they can't access it due to the lack of connectivity. So relying solely on live data quickly becomes a real problem. So to solve this, you might implement a local cache or store using a database like SQLite. But now you've got two sources of truth, both local data and cloud data, and you have to keep them in sync. So you might start fetching periodically to update the local store. And this works if your app only has to read data, and you can overwrite local data with the cloud updates. But as soon as users start making changes while offline, like editing profiles or creating notes or modifying documents, those changes need to be synced up to the cloud. So how do you handle updates occurring both locally and on the server without data loss? In modern apps, multiple users or devices might interact with the same data. For example, working on a document with a colleague, or starting a task on one device and then picking it up on another. So now data is not just changing in two places, but it's changing in many. And synchronizing and resolving conflicts is exponentially harder. Suddenly, edge cases aren't rare, they're everywhere. And the solutions that seem simple at first, they quickly unravel. At a certain point, the complexity is beyond what you can catch with test cases, and it becomes impossible to factor in all the possible code paths. So the edge cases have really become unmanageable. So we've covered how even in a simple app, it can become quickly tangled up with edge cases. But it's not just about app design. There's some fundamental assumptions that we all start with that are kind of baked into how we think about connectivity. And these assumptions, known as the fallacies of distributed computing, shape how we think about connectivity. These originated back at Sun in 1994, and are still very relevant today. In particular, the first two fallacies, right? We assume that the network is reliable, that connectivity is always there when we need it, and we assume that latency is zero, that data is going to flow instantaneously. These tend to be so far from the truth in mobile contexts that it seems negligent not to account for them in our designs. So while our devices have become exponentially more powerful and user expectations have evolved, our approach to connectivity has stayed largely the same. In the early days, we kind of optimistically hoped that Moore's law would apply to connectivity, just as it did to compute, right? Next year, everything's going to get faster, cheaper, more stable, and magically all of today's problems will just disappear. But the edge cases are not actually implementation issues. They arise because of some fundamental logical challenges about keeping data in sync across space and time. So to address these challenges, we really need to rethink connectivity in app design in a way that designs for the reality of these distributed systems, rather than just trying to focus on ideal scenarios. To rethink connectivity, we need to focus on 5 core principles. Connectivity, how devices can connect to each other. Efficiency, how we can move data around between those devices. Consistency, how we sync that data. Security, of course, how we protect it. And most importantly, usability. How do we make this easy to implement for developers? Let's start with connectivity. In distributed systems, devices connect across varied networks, across Wi-Fi, Bluetooth, cellular, and more. Our goal is to build a resilient, adaptable connection layer that handles all of these shifts seamlessly. Efficiency. Syncing all data across all devices will quickly drain bandwidth and storage and battery. So to rethink connectivity kind of from the ground up, we need to design for efficient data replication, syncing only what's needed so that you can reduce the load on the devices and the individual networks. And additionally, syncing large amounts of data takes a lot of time, and as that increases, the risk that your state will change goes up. Consistency. Data consistency is critical, especially when devices go offline or they're in transit. And by designing for eventual consistency, we can ensure the data converges to a unified state without risking conflicts. Security. With decentralized peer-to-peer connections, we face new security challenges. A modern solution must protect against unauthorized access, making sure that only the right devices can access sensitive information. And lastly, usability. Distributed systems really require a shift in thinking The goal is to make these new architectures easy for developers to adopt, so the technology is approachable and it's sustainable in real-world applications. So these 5 principles, connectivity, efficiency, consistency, security, and usability, form the foundation for rethinking connectivity in app design. By applying these principles, we can build systems that handle the complexity of today's distributed environments and meet users' needs in the real world. Next, I'd like to show you an example of this in action. At Ditto, we've developed a platform that embodies each of these core principles, and it handles the complexities of distributed peer-to-peer connectivity. And I'd like to show you how we put some of these principles into practice. To address connectivity, Ditto builds a self-organizing mesh network. Devices automatically discover each other and connect, forming a flexible structure that doesn't rely on any single transport. Our Rainbow connection combines all available transports, Wi-Fi, Bluetooth, LAN, cellular, to ensure seamless, resilient connectivity with fallbacks. And this allows us to handle variable network conditions automatically, as each device in the mesh can adapt to what's best for them. Ditto's approach to efficiency is to only sync what's necessary. And this becomes particularly important when you're working over a narrow pipe. So by transferring only change diffs, or deltas, we keep bandwidth use low and the latency minimal. And this method allows users to make concurrent edits without heavy network load, making Ditto both fast and lightweight on distributed networks. To ensure consistency, Ditto uses conflict-free replicated data types, which you may know as CRDTs, and this technology allows for automatic merging of changes. So edits made offline or across different devices sync seamlessly when connections are restored. And this ensures what's known as eventual consistency. Ditto handles the replication for you based on queries that you define, automatically finding and connecting to devices on the mesh. And this is especially powerful in cross-platform contexts if you want data to move around a network of different devices. Ditto secures each connection with mutually authenticated TLS 1.3, ensuring that only trusted devices can access the network. And each device verifies its identity through a unique key, enabling private and secure data transfer. Using a feature called the presence graph, Ditto dynamically prioritizes secure and multi-hop connections, optimizing for privacy across the mesh. And finally, usability. Distributed systems require a new way of thinking. Ditto aims to make this as simple as possible. To init the Ditto sync engine, it's as straightforward as providing your app ID and token and calling start sync. And this lets developers start building right away on an offline-first, peer-to-peer sync foundation without needing to rethink their entire stack. So next, I'd like to show you an example of this working in the real world. If you have taken a flight on Lufthansa recently, maybe to come to the conference today, your plane took off thanks to Ditto. Lufthansa posed the question, how can we use mobile to improve turnaround times? So for context, in the aviation industry as a whole, these are the 2 main issues, cost on the tarmac and delays. So minutes that the airplanes are not in the air cost hundreds of dollars. And with the delays, those hundreds add up to millions every year. So what can lead to extended time on the tarmac? It can be something as simple as discovering that there's a missing fire extinguisher in the bulkhead cupboard that you only discover as the checklist is being done. And these are very much paper-based processes. And the reason they remain paper-based for so long is because of really low connectivity in these challenging environments. So the value of mobile devices was really greatly reduced, as if they couldn't connect, they just weren't useful. An Airbus A350, for example, is a nearly 60-meter long Faraday cage. So when the airplane is on the ground and Wi-Fi hasn't been turned on, so cellular reception is not reliable. And by using the Rainbow connection, these devices are now able to connect to each other. And multi-hop allows data to flow throughout the aircraft. This solution dramatically reduced plane turnaround time But surprisingly, the business case wasn't actually built on that. The business case was actually made on the paper savings, not the turnaround time, which ended up paying for the development of the app and the operational costs. Lufthansa saves around $500,000 per year on printing costs, which is sort of mind-boggling. Another place that this is applicable, another real-world example is retail. So in retail, you might have different devices serving different parts of the business. For example, a kitchen display for staff, a menu for customers, or a point of sale taking orders. And these systems need to work together so that the orders at the front of the house are reliably transmitted to the kitchen for prep. In busy and complex environments like this, traditional networks often struggle. You'll have a runner who spends their whole day moving between these positions to keep everything running. The ability to reliably form a peer-to-peer network and then move data around is a real game changer for the retail industry. And lastly, the ability to provide connectivity in extreme environments provides some significant advantages in mission-critical situations like emergency responders and field operations. An example of that is the Android Team Awareness Kit, or ATAK, if you're familiar. In emergency situations, teams need to remain constantly aware of each other and share information in real time. And this enables what's called the common operating picture. However, the ATAK system is actually reliant on centralized connectivity, which often by definition is unavailable in these situations. So the EdgeSync plugin enables ATAK to operate across any connectivity environment by using secure offline peer-to-peer data sync. And by connecting across Bluetooth, LE, Wi-Fi aware, radio, and more, Ditto ensures a continuous picture without needing a centralized server. So this is an example of those connectivity, consistency, and security principles in action. So today we covered 3 key steps to creating local-first apps. We started with the key takeaway that there is no happy path. Some hard problems are just hard. And we talked about 5 key principles that maybe you can apply when you think about distributed systems or building in distributed systems. And then lastly, we saw how those ideas came to life in Ditto. So I'd love to meet all of you and hear about what hard problems you guys are working on. Come visit us at the stall downstairs. We're doing a raffle. Thank you.